Hi all, this is going to be a lecture series on numerical in algebra, and this lecture we are going to see about what is least square problems. So least square problems in the language of numerical in algebra is about to solve a matrix equation called Ax equal to b. In this matrix equation Ax equal to b, A normally have more rows than columns. So we have no solutions. The reason is we have more number of equations than the number of unknowns n. So what happens when there is more number of rows than columns means we have a m-dimensional vector space, and the column space is spanned by range of A, where the number of vectors spanning range of A is n, which is typically less than m. So it is a subspace of the n-dimensional space. So obviously B lies in an n-dimensional space, but doesn't most generally it doesn't belongs to a subspace of spanned by the range of A. So what if doesn't lies on the space of A, then Ax minus b is a residual vector, which is normally it should be a zero vector, but in this case it won't be a zero vector. So it doesn't lies in the column space of A. That is the reason we don't have a zero vector residual vector Ax minus b. So we have a non-zero residual vector Ax minus b or b minus Ax, and that somehow that has to be minimized in order to get a best solutions. We don't have a solution, but the best solution is to try to find a vector coefficient vector x, which is a coefficient of b in column space of A, in such a way that that residual norm of that vector r is to be minimized. So we can take any norm, but normally two norm is preferred for somewhat the reason that many of the optimization problems is quadratic problems, where we have to take a derivative, it ends up with a matrix equation X equal to B. So for example, if we are taking a polynomial fitting, we have m data points. So the best polynomial to fit or to make an interpolations would be an m-dimensional or mth order polynomial, which is expressed by this equation 11.3. And in terms of matrix, it ends up with the 11.4 equations called as square van Wandt systems. And when solving this, we are trying to find out the coefficient C0 to Cm minus 1. And this is represented in the figure 11.1. So if for m data points, so we have an mth order polynomial, and which passes through all these data points. But we have one of the problem is this system is very highly ill conditions. The concept of ill conditioning and the condition number, what is stability, will come in the later part of the lecture series. And moreover, even though after if it passes through all these data points, so because of the measurement errors with the unknown data point, the unknown for unknown data point, the value that we have to identify would be somehow oversensitive, and that is one thing. And another thing is the end effects. When we are trying to fit this end effect, this is not due to the because of the way the data is being distributed, but it's the way the how we are fitting this data point using the mth order polynomial. So usually for this data fitting or interpolating, we prefer a polynomial with order of the polynomial much less than the number of data points. For example, n would be very less than compared to the m data points. M will be equal to the number of equations in the van Wandt systems. So we are trying to find out for which we will have a matrix equation which doesn't have any solutions. But at the same time, what we try to do is, in terms of a polynomial fitting, it doesn't pass us through all the points, but we try to find a fitting polynomial of the nth order, which will try to minimize this difference between the fitting value and the true value as far as possible. So this 11.6 of fitting of this polynomial to minimize this error will be equivalent to of the minimizing the residual in as we introduced in the previously, like minimizing the square error for the van der Waals systems. Here it will be the coefficient of expansion for this vector y. Here there it is equivalent to the vector b. So how do we find the solutions? So in the geometrical means B is in an m-dimensional space, and we try to find out the coefficient of expansion in the column space of A, which is a subspace. So we try to project the vector B into A with the coefficient of expansion x, such a way that when the projection during that projection that residual vector R is minimized. The best projections to minimize the R would be the orthogonal projections. So the vector in other sense, what we say is that residual vector which is formed, that B minus AX, which doesn't lies in the column space of A, has to be orthogonal to the column space of A or the range of A. So that is what the round point theorem says, that we try to find us a solution such a way that the residual is minimized only and one if the condition that R is perpendicular to the range of A. So that is what it has been given in the equation is that every column has to be perpendicular to the residual vector R. So this is what diagrammatically it has been represented here. And equivalently, we try to form normal equations 11.9, and that again it is equivalently equal to that we try to find out the projector for the vector B to project the vector B into the column space of A using the coefficient of expansion x, such a way that the P is orthogonal projector. Only then we try to find an optimal solutions for this Ax equal to B, which is now overdetermined systems. So this applies only if the condition, very important condition, that the A has a full rank, because all columns of A are linearly independent. So if A has a column, A has a full rank, then from this equation 1.9 we can try to find a pseudo inverse. And if we find a pseudo inverse, then we can solve the equation for X. That would be gives these equations. So this A star A inverse A star would be called as a pseudo inverse of A, and it can be represented by A plus, and it has n cross m, where it has more columns than the rows. So it is the other way that we have to say is that we are trying to find orthogonal projector such a way that the orthogonal projector is projecting, that it gives you the vector y. So basically, based on this setup, we have a three-way to solve this matrix equations, which is overdetermined. That is termed to be as least square problems. One is the standardized method called the normal equations, where we multiply by a transpose on both sides. Once we multiply, then we take a Cholesky. This is the algorithm. Once we multiply, we take a Cholesky factorization and try to find R transpose or this upper triangular matrix. Then we try to solve Royer triangular systems to obtain the vector W. Then we substitute that into this equations Rx equal to W and try using upper triangular systems. Then we can solve for X. So this seems to be very straightforward, and Cholesky operations takes NQ flops, which is a bit computationally expensive. But the one important criteria, this forming these normal equations is very ill conditions, which will be coming in the later part of the lecture series. The second way is assuming that A has a full rank. We can solve for the modern classical method called QR factorization, either using Gram-Smith organization or Gauss-Euler triangles, which we introduced earlier. The algorithm is similar, like explained in 1.2. Is try to find the QR factorizations and try to once then we try to find the this vector Q transpose B, then Rx equal to, then Q factorization, then we try to find out Rx equal to Q transpose B, which is similar to like this. So the orthogonal projections will be QQ transpose. Then this, as we introduced earlier, the Y can becomes like this. Then Ax equal to B can be expressed in terms of this vector 11.16. Then multiplying by this Q transpose will becomes Rx, it's an upper triangular, then that can be easily solved. So this again takes n cube flops, and with the condition that A has a full rank. So what about if there is an rank deficient matrix A? Then the way to solve this is using a singular value decomposition of matrix A, which will give the orthogonal projection from the left singular vector U transpose B. Then we can express the matrix A is equal to B in terms of this. And once this been done, then we can multiply by U transpose on the left side to obtain this matrix equation. Then again we can solve for the vector X using the diagonalization vector here. So this is similar that algorithm 3, that we come with singular value vectorization, then you transpose B, then W vector is solved for this matrix equations, and that is being substituted here to solve for the vector X. So these are the three-way methods, and comparing this algorithm, the first is a bit speedy, but it's not stable. The second vector is okay, it's a standardized method, but it's not that easy when the A is having rank division or ill conditions. So the only way to solve the ill condition matrix, which is normally happening in the data mining applications, would be to go for an SVD way of solving the least square problems. So hopefully you'll see about the what is the conditioning and stability, the next part of the lecture series. Thank you.